Welcome back. I have a door here. You can see its dimensions in the image. You have a wall on the XZ plane. Also, there is a cable that connects the corner of the door at point A and the point B on the wall. That cable holds the door open at 15 degrees. Due to the tension force in the cable, the door experiences a force vector of 200 newtons that originates from this point A, and it points in the direction of point B. And now, here's the thing. If I compute a moment about point O in the origin of the coordinate frame, due to this force, then I will have a general moment vector about point O that looks like this, more or less. However, it's not that useful to me because the door can only move about the x-axis. And that said, you can see the two hinges here. So I'm more interested in finding the component of the general moment vector in the x direction, which would be something like this. So that's what you need to compute, the component of MO along the x dimension. And now a small hint. In order to do it quicker, think about how you can use the dot product to achieve this MX component. So good luck, try it out by yourself first, and then see the solutions in the next video. Thank you very much. Welcome back. Let's now find the component of the moment about the x-axis. First of all, let's find a general moment about point O due to this force F equals 200 newtons. For that, we need to have a position vector from point O, from the origin, till point A. And then we also need to decompose this force vector into its I, J, and K components. So here you can see the X, Y, and Z dimensions, but here I will simply draw the YZ plane. So the x-axis goes towards U. And now, you know that the width of the door is 1 meter. It's this one here. And then the door itself is lifted up at 15 degrees. And so if you were to close the door, then it would be here at y equals 1 meter. So that means that this side here, that's also 1 meter here. And with that, you can get the y and the z coordinates of point A. It's this one here. So this one, it would be YA, and this one, it would be ZA. YA equals 1 times cosine 15 degrees. It will give you this answer, or approximately, it will give you this one. And then ZA equals 1 times sine 15 degrees, and it will give you this answer, or approximately 0.2588 meters. And then you already know that XA equals 2.5 meters. You can see it here in this image. Your X is at 2.5 meters. It means that the position vector from point O to point A, that we can simply call ROA, it will be 2.5i plus cosine 15 degrees J plus sine 15 degrees K, and that would be in meters. Then we also need to have a position vector from point O to point B. So ROB equals 0.5i plus 0j plus 2k meters. Thus, the displacement vector RAB equals ROB minus ROA, and it will give you this result here. That's the displacement vector that goes from point A to point B. Then the magnitude of this displacement vector is this one here. You square all the terms and then you square root them here with this 1/2 power. Now this term here, it can be written like this. 4 minus 4 times sine 15 degrees plus sine squared 15 degrees. It's simply this case. A minus b squared equals a minus b times a minus b, and you will get this result, or simply this result here. That's exactly what I did here. And so that means that the magnitude of this displacement vector, it can be written down like this. And now look, this one here, this is a trigonometric identity, which is 1. And so 4 plus 1 plus 4 will give you 9. And so this will be your final magnitude of the displacement vector, which is more or less 2.82 meters. So I'm just going to write it here. This is the magnitude of your displacement vector. And now we can use all that to decompose this force vector. FAB vector equals the magnitude of that vector times the general unit vector, which is in this direction here. So it will be 200 times, and then all that. This is your general unit vector, and that's the final result of the decomposed force vector. And so the moment about point O equals the position vector OA cross FAB. And you already know how to calculate that. This is your 3x3 determinant. Remember that this one here, that's this one here, and then this one here, that's this one here. And so you will have I times all that, then minus J times all that, plus K times, and then all that. And in the end, this will be your final result. This is your moment about point O. And so you have a general moment about point O, which is approximately this one here. In the XYZ coordinate frame, it looks like this. This is the X component of the moment vector. This is the Y component of the moment vector. And then finally, this is the Z component of the moment vector. And so in the end, this is your moment vector here. Now, you already see that the X component of that moment is 137 Newton meters. However, let's get that number in a more generic way using the dot product. Remember that with a dot product, you could have a general unit vector and another vector, let's call it F, and then you could project this force vector F onto this unit vector using the dot product like this. F parallel equals F vector dot and then U vector. And then of course here you have 90 degrees. In our case, we can define a unit vector in the X direction. So let it be this one here. Let it be UX. And this unit vector equals 1i plus 0j plus 0k. And now I can get the X component of the moment vector like this. MO equals, then this is the position vector OA cross the force vector AB. This is what gave us this one. However, now I will take all that and I will dot it with UX. And so in the end, I will have this moment vector dot this unit vector, and that will give me 137 Newton meters. Now in this case, it was not necessary to do it like this. Once you had your general moment vector, you could simply take this 137 from here. However, the power of this formula is that I can define any unit vector in the 3D space, and I can project my MO onto that unit vector. For example, what if I had a unit vector which equals all this, and now I want to project this moment vector onto this general unit vector. And so in that case, it will look like this. The moment vector projected onto the unit vector, it equals, that's the moment vector, that's the unit vector, and you dot them, and then you will have this result. And if you add them all together, then you will have 448 over square root of 3 Newton meters. And so this is the moment that is projected onto this general unit vector. So this vector here, that's MO, then this would be the general unit vector, U, so it would be this one here. And so with this dot product, you take this moment vector and you project it onto this unit vector. So this one here, that's your MO projected onto U. And remember, this number here, it's a scalar, of course, because the dot product gives you a scalar. Thank you very much. Welcome back. I have a caster wheel here. It experiences a 500 Newton force from up and down. The perpendicular distance between their lines of action is 50 millimeters. If you remember, then we earlier had a rod that was subject to two forces with equal magnitudes but opposite in direction. So this was F and this was F. And then the length of the rod was d meters. That was a special case where the rod would only start rotating, but the center of mass would not accelerate anywhere. We called it a couple moment that you could calculate by simply taking one force, F, and multiplying it by the entire length between these two forces. And this length, it had to be perpendicular to these two forces. And then, equivalently, I could simply replace these two forces and this distance with a couple moment notation, which looks like this. So this would be the moment about the center of mass. It would be F times d. In this case, it would be counterclockwise. And if you look at our caster wheel, then here you too have a couple moment that is counterclockwise due to these two 500 Newton forces. So here the moment would be 500 newtons times 50 millimeters. That would be 25,000 Newton millimeters. And of course it would be counterclockwise. However, that wheel is not rotating anywhere, which means that there must be another couple moment that counters it. And there is. You have two forces here, F and F. Again, they have the same magnitudes, but they are opposite in direction. The perpendicular distance between them is 40 millimeters. So the question to you now is, what is this F force so that the resultant moment on the caster wheel is 0 Newton millimeters? You want the resultant moment to be this one. What kind of force do you need to have for that? Try it out by yourself first, and then see you in the next video. Thank you very much. Welcome back. So let's now find the force F for the caster wheel. Remember, the objective is to make the resultant moment 0 Newton millimeters. Since the two vertical forces create a counterclockwise couple moment, the two horizontal forces need to create the same couple moment, but it has to be clockwise. So let's put here mv, which means that this moment is due to these two vertical forces, and then I'm gonna write here mh, which is due to these horizontal forces, and so it would be F times 40, and it's of course clockwise, and so the resultant moment needs to be mv plus mh, or 25,000 Newton millimeters counterclockwise, minus F times 40 Newton millimeters clockwise, and that's why you have this minus sign here, and it has to equal 0 Newton millimeters. That means that F times 40 equals 25,000, so F equals 25,000 over 40, and that would be 625 newtons. And there you go, the horizontal forces, they have to be 625 newtons, and they have to be in this configuration where they create a clockwise couple moment, and then these two couple moments, they will neutralize each other. This one will be neutralized by this one. And notice that here we didn't calculate a moment about a certain point. That's because we didn't have to. We simply had to neutralize this counterclockwise mv moment with a clockwise mh moment. If these two forces, instead of being here, if I had put them here instead, so this is F and this is F, and let's say that now their distance is 20 millimeters between them, then of course your F would be 25,000 over 20. That would be 1250 newtons. So this is 1250 newtons, and this is 1250 newtons. But now, this couple moment is about this point here. Before, it was about this point. It was the middle of this perpendicular distance. You had 20 here and 20 here, and also horizontally it would be in the middle. However, now this couple moment is about this point here. So this would be 10 and this would be 10. You can see that it's about another point. But when you deal with couple moments, then it doesn't matter. You can see that it will give you the same effect. The resultant moment will be 0 Newton millimeters in the first case, and also in the second case, where you have 25,000 minus F times 20, where F equals 1250 newtons. In that case, your resultant moment would also be 0 Newton millimeters. And that's why in these kind of statics problems, we don't have to specify the point about which we are taking our couple moment. Thank you very much.